So welcome everybody to this webinar, Europlanet Webinar. We'll talk about Enceladus, exciting results from Cassini, and upcoming new ideas for mission to Enceladus by ESA. This webinar is organized together with the COST Action Planets. So COST is the collaboration between science and technology in Europe. It's European funded. And this is a little bit new. Cost is not new, but the collaboration is new. And so Alexandra Lehtmets here is from Cost, and she will explain a little bit about the context. So Alexandra?
Thank you, Martin. I'm representing our Cost Action Planets, and basically Cost Action, as Martin said, is European funding organization that supports collaborative research and innovation networks across a wide range of scientific disciplines. And one of such initiatives is ours, which is Cost Action Planets, which focuses on understanding how planetary systems form. Observations of protoplanetary disks reveal complex structures like rings and gaps, raising key questions about when and how planets emerge, especially given the low observed disk masses and the surprising diversity of exoplanetary systems. And to tackle these challenges, the action brings together experiments, models, observations within a coordinated European network, aiming to build a more complete picture of solar system formation while supporting collaboration, training, and knowledge exchange.
So today we talk about Enceladus. Next to Saturn, we're going there with Nozair Khawaja and with Jörn Helbert. So Nozair leads a science research group at the Freie Universität in Berlin. He focuses on the exploring habitability of ocean worlds, such as Enceladus, and cosmic dust using space mission data and laboratory simulations. He's associated with multiple missions, Cassini, of course, the Europa Clipper mission. He's also PI of the European Research Council-funded Consolidated Grants project called AIMS, and AIMS stands for the Analog Icy Moons simulations. So he's simulating this in the lab. I think we will hear about that probably in the talk. He's a co-I on space-based mass spectrometer on board the JAXA Future Destiny mission and the Future Asteroid mission to Thetum. He's also a co-I on the Bioscience project, and perhaps he will talk about that as well. So Nozair will do the first talk, and then Jörn will do the second talk. And Jörn is currently he's the head of the solar system section in the science directorate at the European Space Agency. He is a study scientist for the L4 mission to Enceladus, and that's what he will be talking about today. His background is in understanding the composition of planetary surfaces using remote sensing information. Before he joined ESA, he worked more than 20 years at DLR in Berlin and was involved in a wide range of missions with ESA, with NASA, and with JAXA. So without further ado, Nozair, I hand the floor to you.
I'm going to talk today one of the main questions that we would like to address whenever we talk about the habitability, and particularly the habitability of ocean worlds, that we would like to know that whether there are organics or not. And if there are organics, then what are those? So Enceladus is the prime object. So that's why for exploring the habitability. And that's why the question that whatever we knew from Cassini, what is the current status right now regarding organics and how we were able to detect those organics. So I will also talk about, because it is very much connected with Martin just said about ERC Consolidating Grant Project, because this is there where we are heading to explore the habitability of Enceladus using laboratory simulations. So just to give a little bit background here, to give one glance that what was the duration of Cassini-Huygens missions. It was 1997. That was the time when it was launched until 2017, when sadly Cassini was ended. And the rendezvous of Cassini at the Saturnian system was approximately in 2004. when it arrived in Saturnian system, and then it started to explore what we now about Saturnian system, and as well as a lot of things about Titan and Enceladus and other icy moons. So another background slide here, just to give you a little bit glance that you have planet Saturn, then you have many rings, many small moons, and one of the diffused outer ring is the E ring that you can see here, extended, for example, from, let me pick the, okay, so you can see my mouse probably, yeah. Okay, so you have Mimas, you have Enceladus, Tethys, Dione, Rhea, and if you go further to the right, then you will have Titan. So these moons are really embedded kind of in the outermost ring of ice particles, micron-sized particles. And if I zoom this, for example, it seems like my slide is okay.
It works.
Yeah, it works now. So if you look at that encircled Enceladus, which is about 3.95 Saturnian radii, and if we further zoom in, then you can see that you have the E ring, more closer look, and on Enceladus on the right side, the south pole of Enceladus is really very active here because it is emitted a lot of material, whatever the material it is coming from the subsurface regions of Enceladus. So that's why it is really very interesting, because we think that it is the only one extraterrestrial ocean world so far from where we have captured the subsurface ocean material. If you look at Enceladus, the interior, you can see really deep inside is the rocky core, which is quite porous and unconsolidated, and ocean is on top, which is percolated inside the rocky core. And then you have the icy crust on top. If you look at the South Pole, which is now towards the north side, I just make it like that. So you have the icy crust and the vents and the cracks from where this material is coming out. So it means when you have the water rock interactions, you have the pH about 9 to 11 here. The surface temperature means the temperature at the bottom of ocean or in the top layers of the core is about 90 degrees centigrade, and the pressure will be about of the same order, about 80 bar. That actually trigger a lot of interest to this body, because when you look into the Earth's oceans, you can see to the Lost City hydrothermal vent and Prony Bay hydrothermal field, especially these two hydrothermal vent systems, where you have quite similar conditions that we have found on Enceladus. And here you have a lot of organics, a lot of microbial life in Earth's oceans that we have found already. So that means it is a natural, inclination towards Enceladus, that if the conditions met there, then potentially we can have some biosignatures, or maybe we will find life if life exists there. So now we are moving towards more that what we know from Enceladus using Cassini instruments, and what is the significance of the interior of Enceladus, whatever we found outside in space emitting from Enceladus. So if you look into the cross section on the very left side, the top is the core, and then you have ocean, and then you have icy crust. And you can see that the water is percolated in the core, where a lot of reactions are happening, and then this material is transporting through the ocean inside the icy crust. And then finally, this is the water table, where actually most of the physical process is happened, means that you have ice grain formation and the gas grain interaction with the icy vent walls, and then finally you get the material outside. And if you see the gradient conditions, the temperature and pressure, you have a lot of temperature and pressure inside the core, and then gradually you are decreasing, and finally you have the triple point of water conditions in this water table. And that has quite some significance. Whatever you detect in the plume or outside Enceladus, it is really affected by the physical and chemical processes, whatever is happening inside Enceladus. And of course, those processes are dependent on the conditions as well, related to temperature and pressure. So just to give you another view, if you look on the left side, then you will find that we have 4 fracture zones on the south pole of Enceladus. And these are the fractures which are directly connected to the liquid water ocean. On the right side, you can see a very nice image from where these particles are emitted. And this is the area that we are really focusing on. It depends on that where Enceladus is orbiting around Saturn, at what location it is. It depends on how the Saturn is exerting its gravitational force, its perihelion or apohelion, and then the activity from the subsurface can be triggered a lot or can be decreased accordingly. But this is the source of whatever the material we are observing is coming out from this region. So now we are coming outside. You know the story inside, that how there are variable conditions on Enceladus, and now we are the outside, the topic of today's talk, that what kind of organics that we have so far detected. And you can see that plenty of molecular structures that I have listed here. So let me go through, for example, the gases that we have detected through Cassini's instrument. We have CO, we have HCN, we have CO2, we have argon. Similarly, there are many hydrocarbons, volatile species, that is C2, C3 species you can see here. Then, of course, we have alcohols that was detected. Then we have inorganic species as well. For example, mineral particles, SiO2, nanosilica particles. We have salts, sodium, chloride, carbonate, and phosphates. Then we have carbonyls, which are very fundamental in many biogeochemical reactions here. The carbonyl functional group, C double bond O group here. Then we have amines that we detected, ethylamine, methylamine, or maybe some other amines, but we cannot tell with confidence. And the most interesting thing is that we have also found the complexity of organics, that is aromatics. Sometimes we have single ring aromatics, sometimes we have really complex aromatic structures that we have found. So the question is that how did we detect these species? There were 2 mass spectrometers on board Cassini. One was on the left, INMS. It was sensitive for the volatile and gaseous species. And then we have a cosmic dust analyzer, which was the dust mass spectrometer, and it was sensitive for the ice particles that were emitted by Enceladus. As I mentioned, that INMS was only sensitive for the gas phase species or the volatile species here. And the status of organics that INMS has produced is this on the right side in this table. You can see that there are a lot of gaseous species in one column, and then in the other column, you have hydrocarbons, nitrogen-bearing species, with the increasing complexity, oxygen bearing, we have NO bearing species. So these are all species that were with a relative confidence limit was detected by INMS. But here I am more focusing on further status of organics in ice particles. On the right side, you can see here that was detected by cosmic dust analyzer. So the question is that this instrument, cosmic dust analyzer, is the mass spectrometer, similar, I mean, as INMS was the mass spectrometer, but it has a very unconventional way of ionizing the particles. I will let you know in the next slide. But the point is here that the ice particles that were emitted by the south pole of Enceladus, most of these ice particles, they are leaving the Enceladus, and only very less particles are leaving Enceladus, and most of the particles, they fall back again onto the surface. Whatever the particles that are leaving from Enceladus is about 5 to 10%, and they are residing then and form this ring that is E ring I showed you earlier. So the cosmic dust analyzer detected the particles in the E ring as well as detecting the particles directly through the plume. So that means we have a free sample of subsurface ocean that can be collected and that can be sampled in the E ring as well as in the plume. So the basic principle of this instrument, the cosmic dust instrument, is the impact ionization. As I said, it's an unconventional way of ionization where the particle at a hypervelocity impact enter to the instrument, and then by the kinetic energy it vaporizes and ionizes, and then we detect. So for example, it's a little animation. If you can see that the dust particles entered, it hits the target, then the ions are accelerated towards the mass spectrometer, and then finally we get the mass spectrum that you can see it here. This was the story, this was the animation related to the cosmic dust analyzer in space, but we need certain analog in the lab as well, so that whatever the data we collected from space, we can really simulate to identify whatever we claim from space. On the left side, you can see that again, the dust particle, it's just the cartoon. Dust particle enter, hits, and produce the ionic fragments. And here in the bottom is the spectrum of water ice particles that we got from space, from CDA. On the right side, we have the lab in facility, which is laser-induced liquid beam ion desorption mass spectrometry, where we actually use the liquid water solutions bombarded by infrared laser, and it also produces similar ionic fragments, similar to what we got from CDA. And you can see in the bottom that we have the lab spectrum of the water ice, similar to the water ice particles, and you can match very well these species. And this is how we used to identify the species that we got from space. And this is the first result that in space from Enceladus. In the ice grains, we got amines. On the left side is the mass spectrum of CDA of the positive ions. To make it very easy, I color coded it here. The blue stripes are related to the water signatures in the mass spectra. On the green, we have the signatures which are relevant for the amines. And the yellow are the one which are the other organic features associated with amines. And if we simulate the species, for example, here we have butylamine, and then you can see that the green stripes and the yellow stripes are matched very well. So this is how we identified, after a lot of experiments, we identify these features, and we could correspond these features from the space data to the lab data. Then we have aldehydes and ketones. Again, on the left side is the spectrum from space. Just don't go in a lot of complexity, just focus on these green stripes here and match them the green stripes of butanol, which is we tested in the lab, and many other such species we have tested, and we concluded that whatever we observed in space is actually coming from aldehydes and ketones. In general, you can imagine carbonyl species we have detected, and they show this kind of feature in our data. Then the more complexity is to the aromatics here. On the left top is the very complex spectrum of the very complex species, And the species look like on the right side that I have given here. Many, many aromatic compartments, then connected with lot of side chains. How you interpret this, if you look the orange stripe here, that actually reflect to the aromatic benzene or phenyl cation. And then you see this series that we detected, and this is relevant for homologous series that can be produced if we have really gigantic organic molecule connected with lot of aromatic ring structures. In the bottom, again, we have the aromatic data from space, and this belongs to certain small aromatic ring molecules that we have detected. So you can see that how much complexity from carbonyls, amines, and then aromatic we have detected coming out from Enceladus. So the question is, whatever we knew now until now that I showed you, what does it mean where we have the subsurface ocean, which is connected with the rocky core, and the temperature and the pH we have given here. So we think that many complex network of the reactions can happen on Enceladus. And one of them is that if oxygen bearing species are there and they react with aromatic ring structure, in the presence of ammonia and hydrogen, then it leads to the proteogenic amino acids. So this is kind of a Friedel-Crafts type reactions. So it means we could produce such species there. Similarly, if we take this yellow path and then we end up with the carboxylic acid and amino acids synthesis. So we think that the recipe is there, and most likely with the L4 mission, we would know much more if such processes are happening. So the question was that we thought, okay, we have detected many species in the E-ring, which are coming from Enceladus. Why not we look into the data which is directly coming from the plume? Just a few minutes old data we wanted to look. Here you can see that this is E17 and Enceladus 17 flyby in 2012. I think it was in March 2012. And for you to understand that the x-axis is the closest approach. So 0 is the closest approach when the spacecraft was really at the South Pole over to the Tiger stripes. And you can see that the relative abundances of the blue curve is rising as you go closer to Enceladus. Which is relevant, which is actually correspond to the organic bearing species. So it means that in the plume of Enceladus, we really have fresh organics. And for that reason, we look back in another flyby data to go deep into the compositional constraint. And that was E5 flyby. And the geometry of the E5 flyby is this black line. If you see that minus 10 seconds and then closest approach to the surface of Enceladus, which was 21 kilometer, and the speed by which this flyby was made was about 18 kilometer per second. And what was the result? Which was the latest result was these species that we have found, and these spectra correspond to the ether compound, alkene compound, and NO bearing compound like pyrimidine and thiamine like structures. The orange stripes are the characteristics of these compounds that I just listed here at the top, their functional group. And the main point is here that these are very fresh grains, about 5 minutes, a few minutes old, a couple of minutes old when the spacecraft captured them. And these are the representative structures that we think that we have found just recently. If you look into these recently fresh plume particles, then these are the functional groups. And we match actually quite well with CDA and INMS data together. So definitely INMS detected the gas phase species, volatile species. Potentially, these species could be condensed into the ice grain, or they could be more complex organics, and we are just detecting part of that because the ice particles, when hit, it fragmented, and this is how the species can be fragmented. But at least we have detected the functionalities of those complex organics. Just a very quick, I'm not spending time onto these tables, just to give you that what is the current status in the recent results from ether, ethyl, ester, alkene, and NO bearing species that we have found. It's a nice guideline from where we can move on to understand the complexity of organics. So now the question is that earlier I showed you that what does it mean, what we have found, carbonyls, amines, and aromatics, and then the new organics are added into the list. So when we look all organics into the list, then we think that there is a very complex network that is happening in different depths inside Enceladus. And you can see in this box that we have just laid down, it's a quite some references that we have used here. One species can lead to another species under Enceladus conditions, under hydrothermal conditions, to form more complex aromatic species. Similarly, we can form amino acids, and this could lead to really some biological relevant organics if we connect all these dots. This is just a simplified figure of this. You can see that the complex network can lead to many aromatic species. They could lead also amino acids because we did not find all in this puzzle, but we really find quite some that can connect one species to another. And finally, we have more biological relevant organics at the end. So the question was that we wanted to simulate such conditions with our in our lab, and we already started doing this, that what happens with the water rock interaction, as many other labs they are doing it. And this is our laboratory setup where we can simulate up to 150 degrees, 150 bar pressure, and to simulate that what are the output, what are the degradation product of organics and minerals we can identify. And this was our paper in 2024, where we used triglycine. Again, it's a very complex mass spectra, but just to let you know that when we did not process triglycine and we measure it with our mass spectrometer, we only identified 6 species. But after the hydrothermally processed, we got 8 species. So that means whenever we go with the space mission, we should understand that even if we don't identify triglycine, we need to follow the path. We need to trace certain features of triglycine that can lead us to the conclusion of what we have found. So just a few slides left, but give you a gist of what we have found and where we found. So this is the one area that I highlighted, that the particles that we have found was in the E-ring that were coming from Enceladus. Similarly, in the recent work, we have also found the organics in the ice particles, which were really very young, not as older as they were in the E-ring. And the point is here that on the left side, we have found the organics that were years and hours older particles. We detected them through the spacecraft when they enter into the instrument less than 12 kilometers per second. And then we have detected the organics when they were collected at 17, 18 kilometers per second, but their age was very fresh. And we found that the presence of aromatics in the older particles and the presence of aromatics in the young particles really suggests that the origin of these grains were the subsurface from Enceladus. That is the obvious conclusion here based on these results. Just to let you know that Raghu and Benu also detected quite some similar compounds like aromatics, amines. So that might tell us that maybe the core of Enceladus could be related similar to these asteroids, and this will open up the new area of research that we are leading right now. So entering to the last stage, a couple of slides to let you know that, okay, the question is that whatever we have detected, how it can be translated to the subsurface material. You have detected at the South Pole and in the E-ring. The question is that the composition of this can be translated to the icy crust, ocean, or the core, because coming from the initial conditions from the core and detecting in the plume, it's a long journey, right? And there are many gradient conditions that could really change the fate or the type of the composition. And we have to trace it back. We have to track any change that could come. And that track and the tracing of any potential change is done by this ERC project that Martin in the intro mentioned, AIMS, that is Analog Icy Moon Simulations. It's the simulations of the water rock interaction, then the ocean transportation, and then the ice grain formation. This is how in each step we will trace the any change or the synthesis of these chemical species until they are ejected into the plume. Only then we can really tell that whether the spacecraft, whatever it is detected, is corresponding to the subsurface habitats or not. And all this project is now going on. It's just a new project. And here is the group, AIMS group in Berlin. We have Thomas, Joseph, Quentin. Thomas is doing, we are approaching this problem with the quantum chemistry point of view, then aromatic ring at high pressure temperature. Then we are simulating water rock interaction, machine learning, many complex organics that we are going to simulate with our facility. And I will end my talk by handing over this message to you. Now, Jörn Helbert, the stage is yours. Thanks for your attention.
Yeah, thank you. Thank you, Nozair. That is the perfect setup, and I hope you can see my slides. So that makes my talk so much easier because I don't need to convince you why you're going to go to Enceladus. But still, let me just take you one step back and how L4 comes together. L4 stands for the fourth large class mission of ESA, which is basically the flagship class missions of ESA. And we had the Voyage 2050 program, which is the big outlook of where we're going to go in ESA in the future in the science program. And we identified in that one 3 new large class missions, L4, L5, and L6. And the topic for L4 is the moons of the giant planets. And so now you should be aware there are many moons of the giant planets. So we actually had an expert committee that was looking at potential targets and looking at potential moons. And there's an expert report that you can actually read, and there's a QR code here if you want to go on the website. But basically the ranking, I mean, as you would expect, the top ranked candidates were Europa, Ganymede, Enceladus, and Titan. And then the ranking was based on science as well as novelty in a way of looking at who else is going somewhere, because you don't, I mean, it would be nice to go again somewhere, but it would be even more nice to be the first to go somewhere. And I mean, after hearing the top runners, yeah, it should not be any surprise that Enceladus was the by far highest ranked target in terms of science, but as well as in novelty, because we have Europa Clipper going to Europa, we have JUICE going to Ganymede, we have Dragonfly going to Titan, but currently there is no one else having concrete plans to actually going to Enceladus. So it ranked high on both scores. I took out all these slides that I normally have in here because Nozair gave a much, much better talk on why we think this is a habitable world. It has all the characteristics of the habitable world. And so we're actually going to go and look for biosignatures for signs of life. And then in my view, this is interesting in both directions. I mean, of course, we hope we'll detect signs of life. Fantastic, because habitable world, and then we would actually have the first-time proof of life outside of Earth. And that would open up a whole area of questions in terms of exoplanets, other bodies in the solar system. But even the negative answer, if we go there and we don't find any traces of any kind of life, would be interesting in a way, because it would tell us that there's something we are fundamentally misunderstanding on how habitable worlds work. Because this, by all characteristics, Nozair explains this in detail, is a habitable world. So that is basically our driver for the L4 mission. Now, the expert committee not just said, well, you should go to Enceladus, but they also made recommendations on how we should go there. And as you have seen, there is a lot of things you could learn from Cassini. So flying just an orbiter, again, Cassini 2.0, would be nice, but would not be the next big step you want to do. So the next big step you want to go should include a lander, should actually go to these active regions, go to the surface and actually get enough sample, should also do enough flybys. And they explain why flybys through the plumes and sampling the plume material is so absolutely fantastic. So we really want to go the next step, which means we need to develop new technologies. We need to invest a lot also in miniaturization. So let me go kind of start from the end. Start with where we are currently in our mission concept, and then I'm going to go what that means. So this is basically what we are currently have as one of the concepts that we are studying, which is a mission that will be launching on two Ariane 6-4 rockets, an assembly in orbit, just because it will be a really big spacecraft with orbiter and lander. So you need to launch it to actually get the mass up. We're going to go into Saturn orbit. We're going to do a tour through the Saturnian system, fly by basically all the moons that Nozair also was indicating in his talks, all the way down to hopefully Mimas. We're going to do several flybys through the plumes early on, already get signs, already get the first great results. Then we're actually going to go into an orbit around Enceladus, mapping the South Pole area in detail, and then the highlight at the end, we're going to release a lander and bring a lander down in the South Pole region of Enceladus to sample material on the surface of the moon. So this is kind of the concept we are working on right now. The timeline, roughly speaking, we're kind of going backwards. You want to land on Enceladus South Pole area while it's in sunlight. That is about mid to late 2050s. So this basically sets your landing point. And then you can go backwards. So we have about 3 years sampling and going tours through the system. Means arriving around at Saturn around 2050, means launch around 2042. Means if we want to get the whole spacecraft built, test certain anything. So we have an implementation phase currently of about 7 to 8 years, which means we need to do the mission adoption, which is the moment we're really starting to build the spacecraft and everything around 2034. So that's about 8 years from now. And suddenly that landing in the mid-50s, that sounds very far away, suddenly it's tomorrow. Because if you didn't go backwards, it's like, wow, we really need to speed up things. Luckily, we had the ministerial conference last year, and whoever who followed the press conference has seen that the first thing that our Director General was presenting was a mission to Enceladus. So there is a strong momentum in Europe to really push this forward. I talked about this already, but just as a compressed version, this is the timeline actually of the mission. Launch in 2042, the assembly in orbit. We're going to go about 8 to 10 years to Saturn. Orbit insertion, the flybys, the moon tour, reconnaissance, and then actually sitting on the surface for about 2 to 4 weeks, and then dispose of the spacecraft to follow planetary protection guidelines. So as I said, we're going backwards. Looking at that, there's a number of drivers for the mission. So as I said already, launch capabilities. This is going to be a European mission. We're going to go with European launches for now. And so we need to look at launch capabilities. One way to do this right now is actually doing a dual launch and then assembly in orbit. We're going to go solar powered for this mission, which has advantages and disadvantages. The advantage, of course, is it's a known technology. Since we're going to go with solar electric propulsion, we need solar cells in any case because that runs off electric propulsion. And if you do an estimate on power use and how much sunlight do we actually get at Saturn, you come up that you need roughly about 200 square meters of solar arrays, which is huge, but not unheard of huge. So it's bigger than JUICE, and whoever has seen the JUICE spacecraft, it's significantly bigger, but again, it's not unheard of big. And for the lander, we're actually going to go with primary batteries, which already have a high TRL, and here we're actually benefiting from the development for electromobility, for example. Sonar control will be an interesting challenge. Again, electric propulsion produces a lot of heat in the beginning. When we're at Enceladus, we are very cold, so we need to actually deal with this. And of course, telecommunication. I mean, we are far out, so we need to get the data back. So these are the kind of the design drivers. We had industrial studies running, 2 competing studies, basically giving all these kind of things to the industry teams and saying, well, if you are supposed to build this, would this be doable? Would these constraints work? And does this concept close? And the nice result from that was that both primes came back and said, yes, that's technically feasible. They confirmed the size of the solar arrays. They confirmed that the docking in orbit should be doable. And so that means we actually, at this point, have a mission concept that closes. Still is very top level, and now we're actually going to go into details. And so what we're doing this year is now really going into the details of the science traceability metrics, and then actually going to go into Stroman payloads. I'm not going to do a full talk on the science traceability metrics because it would take about 2 hours just by itself, but it's on the website, so you can actually read it. So we had our expert committee and our project working group together. We've been working for the last year and a half to take that top-level scheme and themes and drive science objectives and science questions from that. And the full science traceability matrix is available on our website. There's the links, there's the QR code, so you can go in there and actually look at how we actually subdivided these overlying themes of habitability and interior, self-interior interaction with the external environment, and of course you look at prebiotic chemistry and biosignatures. From that, basically, you get the challenges for the payloads on the orbiter and as well as on the lander. And I mean, of course, power will be one of the drivers. Data volume, I mean, especially mass spectrometer data is quite huge. Camera data is quite huge. So you need to get that back from the distance of Enceladus and the Saturn system, as well as really adopt the mission for icy moons. And for the lander, that's supposed to be an astrobiology lander. So you really need to develop technologies to detect biosignatures with high sensitivity. There's a whole question of cleanliness in both directions. Plenty protection. We don't want to contaminate Enceladus, but also false positives. We don't want to actually take microbes with us and then we just detect my fingerprint on Enceladus as a sign of life. So cleanness contamination is a big question. Autonomy. We are far away, which means we have long communication times. So everything basically needs to run autonomous as much as possible. The whole question of sampling handling, I mean, it's most likely a very porous material. It might also be compacted, so we need to have a sampling handling system that can work with both of that. And all this in a very miniaturized and power optimized format. And I'm just going to talk very briefly about the lander before I close out. So currently we're looking at something that has a self-separation time between 14 and 30 days. And there is a rough timeline of what that actually means. This is one of the configuration that we are looking at for the lander. As I said, it runs on batteries. Roughly 20 kilos of payload and about 120 kilograms of batteries to run this. And that brings you to a mass of between 600 kilo and 1 ton that we're actually going to put down on the surface of Enceladus. And of course, we're landing in something that we have never actually seen close up. So we are not entirely sure what the terrain will be and what the surface property will be like. So we need to have a landing system that can cover a wide range of typical surface properties. And I mean, actually, where and how we land is one of the tricky questions, because we're going to look for somewhere where there's fresh material, where there's fresh deposits. But we have seen from the Cassini images that most of the area looks rough, but it looks rough on the scale that we have from Cassini, which is in the best case down to maybe 100 meter. Our lander will be about 2 meter in diameter. So it will be a very interesting challenge to pick a landing area. And we are looking currently at active hazard avoidance. So picking a region that is relatively safe, and that within that region, the lander will autonomously pick a safe landing site with a guided approach. But of course, there is a lot of pre-work that needs to be done on surface properties, on actually getting this hazard avoidance working on something that's relatively dark, relatively low contrast surface. Which takes me to my final slide and the outlook just for the next 2 years. I showed you the big outlook, and now actually focus on the next 2 years. So we're currently in the process together with the payload working group and the expert committee to work on sets of Stroman payloads. That is to show, we've shown there's a mission concept that closes, and now we want to show there actually are payload complements that would work and would address the science questions. And to give the community again an idea of, okay, here's the science question, here are possible implementations. And then we're going to have a community workshop, and there is a QR code, December 8 to 10 here at ESTEC, where we're going to present everything that we've done so far to the community. And we're actually asking the community to come in and actually present their ideas and say, well, I looked at the science traceability metric, and I have a completely new idea for an instrument that you haven't seen yet. Like, yeah, fantastic. Because that actually then goes into the next phase, where we're actually going to do another industry study now, going into more details, and then opening at some point a phase A call. That depends a bit on the detailed planning that is going on right now. And we should know by about summer this year what actually is the exact timeline of where we're going to go from there. And again, as I said, there is the science traceability metrics, and you see in the bottom how we'll hopefully look at the 2058, 2059 with our lander sitting on the surface and actually sampling the surface material. Thank you.
Thank you so much, Jörn. Thank you so much, Nozair, for wonderful talks and very engaging, because we have tons of questions, which is great. So we'll probably go a little bit over the hour. Just stick around if you want to address all these questions. Jörn, I think you meant, by the way, your last slide, it said November 25. I think you meant November 26, probably.
Yeah.
Coming up. Yeah, right, exactly. Okay. First question was a hand raised, and I will, by Aurélie, and I will allow her to talk right now so they can ask her question. Aurélie, do you want to unmute yourself?
Sorry, I think it was a mistake.
It was a mistake. No question on your end. Okay. In that case, okay, then we'll just go to the next question, which I lost track of the order, but I will just go with the Q&A here. So Solomon asks, this is for Nozair, if there were longer chains carboxylic acids in the icy grains, for example C16, would you have been able to detect them?
Thank you for the question. One thing that we can tell at the moment, that what is the maximum length of the molecule, whether it is long chain or whether it is the compartment of aromatic compartments. So it's about 1,500 to 2,000 atomic mass unit. that so far, with a lot of aromaticity, we have found. And it depends on whether it was a very saturated, highly saturated, or unsaturated carbon to hydrogen ratio in that sense. But as far as the long chain is concerned, that we cannot tell with our data.
Okay, thank you. The next question, I think, is from Akos, who writes, Dear colleagues, especially Jörn, we are planning to produce Enceladus relevant porous H2 snow in laboratory and analyze embedded organics behavior in it to particle irradiation. It would be useful to have some mission relevant personal contacts from the Enceladus related L4 science mission or ESA science core team. Could you indicate somebody who might be interested in this topic, in the porous snow topic, and would it be you?
I mean, yeah, I'm the point of contact for now, and then I can actually forward that internally. So we actually have a group working on that because, I mean, as I indicated, that is a very important topic for variety reasons, from science to pure lander safety point of view and engineering point of view. So yeah, just send me an email and then I can forward the contacts internally.
Great. Adrien is asking, how can you be sure that the ice particle samples in the E-ring are indeed coming from the Enceladus plume?
Right. So there are, I'm just talking about the organics here because there are other evidences as well, but let's talk about organics because of this topic. So the detection that we had organics regarding the aromatics and other complex organics, we have as soon as we are going very far from in the E-ring closer to Enceladus. So this is the first evidence that we have the higher abundances of those species. So this means that as soon as you are coming closer to plume, then you have the higher abundances of those organics that you have detected very far in the E-ring. So this is the first thing. Second thing is that whatever the organics you have found very far in the E-ring, which was years old, I would say, that and the nature of those organics are exactly similar with the nature of organics that we have detected in just a few minutes old grains. As soon as the grains are emitted, our spacecraft actually collected those particles. So this ultimately tells us that there is a relation between these particles and very far particles which are in the E-ring. Having said that, this means that those organics are coming from Enceladus subsurface. Having said that, it does not mean that the radiation doesn't affect organics. It means that which organics actually are affected by the radiations and then changed. This needs to be investigated. But whatever the data we have seen, those organics are similar and hence they are coming from the subsurface.
Okay, very good. I hope that answered the question.
Shall I jump in with the next ones, Martin?
Yes, please.
Okay, so our next question comes from the Q&A, and we have, will geothermal reactions of organic compounds be affected by extreme cold of the ice layer at the top surface? Not specified for which speaker this is for, so if either of you have thoughts on this, I'd invite you to jump in.
So I can quickly, as I mentioned in my last slides, that there is not only the filtering processes happening once you have a very high temperature and pressure geothermal reactions, and then these species are transported through the ocean and hence entering into the icy vent where you have now new chemistry there, the cold chemistry that can happen. So yes, there could be a change for certain species that can play a role coming from the core into the icy vent.
Thanks, Nozair. Our next question comes from an anonymous participant who says, great talk, Nozair. I'm wondering about the complex organic network pathways you presented. Can you shed any light about the most likely pathways and those that might also be relevant of other icy bodies?
Oh, it's a difficult questions, and with AIMS project, actually, we are exactly nailing down the reaction pathways. We are just proposing because there are missing puzzles in between, and we would like to find out those puzzles so that we can confidently can tell us. But right now I can say that Friedel-Crafts reaction should be there, Fischer-Tropsch reaction should also be there. This is most likely reactions other than Strecker reaction, maybe to form the amino acids. So who knows? So we would like to really nail down the missing puzzles to be confident, which is the most likely pathway.
Thank you. Our next question is from Mate. Good to see you, Mate. Mate asks, does the orbital speed of the spacecraft have an influence on the ionization efficiency and/or fragmentation? Do you have quantitative data? What is the approximate abundance of the identified species?
Yes, so for example, the complex aromatic ring structures and the species that we have found approximately of a percent level, we have found the abundances of these species there. And the low mass organics, they are in the variable range from ppm level to the percent level. And this is the abundances that we get. And the second question, that whether the high energy has the influences on the fragmentation. Yes, it is. And for that reason, one of the conclusions from my talk, which I did not talk here today, is that what is the most robust organics that can survive the high and slow impact speed and still retain their spectral feature, and that is aromatics. And that's very surprising for us. Of course, we knew that aromatics are more stable organics as compared to other, but this is really surprising that 18 kilometer per second speed, we still get the similar fragment features that we get about 3 to 4 kilometer per second.
Yeah, and maybe let me jump in here as well from the mission perspective, because we actually impact speed. It's an interesting one because there is a scientific driver that you ideally would be as slow as possible to just make sure you don't break up things. But there's a mission instrument driver that, if you look at the results from Cassini and Nozair presented, impact ionization works fantastically, gives you a good result, but that needs a certain speed, and so you have this kind of competing, conflicting requirements. And so we're looking right now from just completely agnostic at concepts. Can we do something with low speed flybys? What would that mean in terms of instruments, as well as with higher speed flybys, so that we are basically, again, ready for whatever the community is presenting as payload components to say, well, that might work, or that might work, or actually we come up that, well, that branch, we cannot see an option to actually make it work. But we're trying to keep the space of possibilities for the mission design as open as possible.
So let me add on, to this. That's great, Jörn, to mention this. And from the speed perspective, related to the question and what Jörn just said, with the impact spectrometers, definitely we are in a certain range, about 2 kilometer per second onward, which is very nice window of the speed, flyby speed, or the landing speed there. Because for the identification of the organics, of course, we need multiple evidences, not based on one instrument. And this particular instrument can actually produce the molecular feature as well as the characteristic fragment features, which is very relevant for the identifications. And I do agree what Jörn just said. So we look forward to this.
Excellent. Good discussion. Next question by Jean-Pierre. You have not mentioned methane as one of the gases detected in the plumes of Enceladus. Are there new findings in the analyzed observations leading to exclude the presence of methane?
Not really, actually. It's just that I was focusing totally on the solid part of the organics, which was ice particles. But yes, thanks for mentioning this. Methane is one of the species that we have found through INMS in the gas phase. And yes, it's one of the things that could really tell us, and it's one of the conditions that we met for the habitable, let's say like that. And regarding the complexity of the synthesis of organics, methane is the one from where we could probably start synthesizing more complex hydrocarbons, as for example, from Fischer-Tropsch reactions. It could really lead to the high mass organics as well as the aromatic hydrocarbons. Thanks for the question.
Okay. Then we have Nora asking, what reference spectra are you using to decompose CDA mass spectra? The impact speed is quite high and variable, and that affects a lot of fragmentation behavior, especially for organic molecules.
Yeah, thank you, Nora, for the question. Yes, I do agree that the high impact speed could cause a lot of fragmentations. And that's why with a certain impact speed range, we are using multiple analytical techniques. And for CDA, one of the facility that we have, laser ablation, that I showed in my slides, actually it can simulate the similar spectra, the spectra of different speed range from 2 kilometer per second until about 15 to 18 kilometer per second. So for that reason, one of the reference spectra is from Lilbit that we would like to use. But the impact ionization spectra could also get from the accelerators. And currently we have accelerator, but that can accelerate only the dust particle, not the water ice particles. And for that reason, because it's a very high impact speed data that I showed you in the flyby, E5 flyby, and for that reason, we thought the water is just gone. You see that in some spectra, the water was not there at such a high impact speed. And for that reason, we actually explore electron ionization technique. And we found that there were quite some nice match of the fragments with our CDA at this high impact speed with electron ionization.
Excellent. I see a hand raised by Jessica. Jessica, would you like to talk? Ask your questions live. Hope she's still online. Okay, otherwise we'll just wait and go to the next question by Dovidas. How do you determine whether particles are fresh or old? And is it related to a radiation effect?
Right. So one thing is that how we know when we are just collecting the particles really at 21 kilometer away from the plume, from the source, within the plume, but from the surface. That means it's just a few minutes old, and the orbital parameters of the ice particles when they emit from Enceladus also tells us as compared to as soon as you are going away, you can really calculate that how much time it took from one place to very far in the outskirts of the E-ring. So this is how we can tell that the particle's age is just a few minutes or hours or years.
Yeah, and I mean, if I can jump in here as well, because again, I mean, it makes an interesting mission design drivers, because yes, we want to have very low flybys exactly to get fresh particles, but also for the lander sitting on the surface. Unlike, for example, Mars, where you would actually go below the surface because you want to have radiation protected material if you look for life. On Enceladus, the freshest, least radiated material actually sits exactly on top of the surface. And so you basically want ideally to scoop off just the very, very top layer. So that again, I mean, for the sampling mechanisms that we're looking at will make an interesting kind of difference to the classical sampling mechanisms. And again, that's one of the things. There will be a lot of technology development projects coming up. And I mean, one of the things that we clearly need to do a lot of tech development on is sampling systems for this kind of surface material.
Yeah. Thanks, Jörn. Maybe I can add a couple of sentences here. This was a very good point. And just to remind the audience here that the instrument of Cassini were very old and very low resolution instruments. And now with L4 mission, we really aim very high resolution, and that will also help regarding the sampling.
Okay, very good. We have a question by Arunapa. What is the largest carbon length among the molecules detected in the Enceladus plumes or ices so far?
So we think that we have much higher than 200 Dalton, 200 atomic mass unit. And that I said earlier in one of the questions, and the length that we can predict of such species is about 1,500 to 2,000 atomic mass units. So such a big and complex organic that we can so far tell.
Okay. Thomas, you want to go ahead?
Yes, sure, I'll jump in.
Sure.
So Tom asks a question for Jörn. Is there an indication yet of the plume flyby and E-ring traversal velocities for a dust detector?
Well, as I said earlier, I mean, we're basically currently looking at both high-speed flybys, where high-speed flybys are in the Cassini kind of range, so optimized for the dust detector, as well as low-speed flybys that would be below the speed of what the dust detector typically needs to see if there are other kind of instruments. So we basically have both mission designs, because it does have an impact on how much delta we need and how to exactly set up the moon tour, if we include the high-speed flybys or not. But basically, currently, both ranges, so the typical Cassini CDA range, as well as a low, very low-speed flyby, are within the ranges that we are studying.
Yeah. Let me a little bit elaborate to that. As I mentioned earlier in my talk, that the particles that are coming from Enceladus is really a free sample. But of course, they are also exposed by the radiation. But certainly there are the free samples, and in the mission design, the detector result that I showed would be great that we started measurement with a very high resolution instruments. Really far from Enceladus, because this will let us know the validity of certain species if we are detecting in the plume really from the surface and very far. So kind of a validity regarding the habitability and biosignature detection would be great if we can really measure during this mission in the E-ring traversals as well.
Thank you. Next, we have a question from Adrian for Nozair. What are the clues of subsurface origin?
The clue of the subsurface origin regarding organics. Otherwise, we have other, evidences. For example, the detection of salts as well as detection of nanosilica particles. That tells us that they are coming from the subsurface. But as far as organics are concerned, of course, we can do a lot of radiation experiments that can tell that if such species are emerging from Enceladus, that how they can be evolved. But this particular result that I just showed you, that is about aromatics, organics. And those aromatic organics tells us that the origin is certainly for that species is the subsurface, because they were just detected a few minutes or a couple of minutes old, and they can be comparable with the years old grains that were in the E-ring. So both compositions are similar. And this tells us that since the abundances of these species are much higher, just above the surface, that definitely tells that there is no other source than the Enceladus, and it is naturally it is the subsurface.
Thank you. Next, we have a question from David. David asks, could an instrument on an orbiter with flyby sampling be able to perform chirality analysis? If not, what kind of measurement could detect a biosignature robustly?
I mean, if you go in our science traceability metrics, which I didn't go down, you will see that actually under C 2.2, we have the search for any other non-chemical biosignatures, and I mean, chirality is one of those. So I mean, it's definitely within the areas that we are absolutely looking for, and especially on the lander. I mean, on the lander, the advantage is you have a higher amount of mass, which makes all this kind of measurements much easier. I would love to see chirality measurements on the orbiter. I'm very confident we're going to do chirality measurements on the lander.
Okay, we still have a couple of more questions left. If everybody's happy to stay, we still have almost 60 attendees, so I guess we can just continue a little bit more. So it's an interesting topic, so much engagement here. Nimisha is asking, how likely is it that you can do plume spectroscopy with a flyby? Also, since ESA recently released the STM for L4, does ESA already know which instruments they do want on a lander?
Maybe I can start with the STM question, then you can talk about the spectroscopy. So no, it's exactly the other way around, and we are doing this how it should be done textbook-wise. So we have science questions. We broke them down into we have themes. We broke them down into objectives. We broke them down into questions, and that are the questions that the mission is supposed to answer. Now, internally, we are looking currently within the Stroman payload process just to make sure that there actually is a payload complement, or ideally a set of payload complements that would work, that we don't have a question where we already know now there will be no way you can actually ever answer that. However, that does not in any way do any pre-selection of instruments. There will be an open call for that, and all we do right now is just make sure there are options, and we will give them also to the community as examples that we came up with this. And this is also, and as I said before, and you should look out in the ESA star system for that. So there will be a lot of tech development activities, because we already see chirality measurement. I mean, there is very high resolution mass spectrometry. I mean, there's a lot of things where we already now see they're instrument concepts, but they need maturation to actually be able to fly in space or to give us the robustness that we need. And so we will go out with a lot of this kind of course. And so the other thing that we use that Stroman payload for right now is to say, well, in principle, there is this kind of instrument that in principle would do it. However, it still needs this kind of development. And then we would actually go out with that and actually try to see and fund development to mature the technology to a level that we can actually then fly it on the L4 mission.
Yes, and for sure, the spectroscopy is one of the tools that can be used for organics and the surface features regarding the composition, as well as potentially through the grains. But this is a matter of the resolution as well, that how advanced we have the instruments. On Cassini, we did have the certain spectrometers, which gives us some compositional information.
Excellent. Thomas is asking another one for Jörn. Will the instrument call be open to ESA member states institutions only, or will it be global?
I mean, the normal way how the science program works is that we as ESA provide the mission, the orbiter, the infrastructure, the launch operation, and the member states provide the instruments. So from that perspective, it will be something that will be open to the member states. If there would be agreement also for partner, I mean, as we've done on many other missions, that's very, very possible that also partners could provide instruments. But of course, I mean, the first call for us goes to the member states, because they're in the end the ones that are providing the payload.
Yeah, understood. Try to do this in chronological order of arrival. There's an anonymous attendee who asks, thanks, Jörn. Are there already some working on the surface material properties of the possible landing sites? If so, how can we get involved?
I mean, one of the things, this had as close already, we had a call out that just closed about 2 or 3 weeks ago, asking the community for work on topography models, for example, because that's one of the first things to go back and actually look at how much we can learn from the existing data and topography models. But there will be more calls coming out for that, looking into the aspects as we go forwards. And if there's anything specifically, just send me an email and we can always discuss things and see how this fits into what we're working on already. And as I said, community workshop, 8 to 10 of December this year. Come and present your things also there.
Thanks, Jörn. We have
the last three, I
just
think.
we have just 3 more questions to answer. Our next one is from David, who asks, is the preliminary concept of a 600 kilogram wet mass lander and a 20 kilogram payload already a fixed architecture, or is that open to changes?
No, it's enough. We fix. It's one that would work. Everything we've done so far is just to make sure there is something that actually would work. And the 20 kilo payload was 600 kilogram lander. That is one of the things where we're pretty sure that would work. And then this will evolve as we go forward in the mission study.
Thank you. Our penultimate question comes from Fulvio in the Q&A section. Fulvio asks, we're working on terrestrial analogues of Enceladus, especially focusing on the use of MS on ice for detection of C isotopes. Is there anybody at ESA interested in this topic?
Yep, absolutely. Again, send me an email. And I mean, this also would be great for the community workshop, because this is really one of the things where it then more or less goes straight into all the payloads in the end.
Thank you. And our last question comes from Helen Grant, who has a question for Jörn. What will your method of sample collection be on the surface? If scooping, how can you be certain the material will not be too solid and that it actually originates from the plumes?
Okay, you have another 3 hours. Sampling of the surface is as I said before, is a really interesting topic, because we actually don't really know the surface properties. So what we are looking at right now is to actually have redundancy in that we're using planning to use various surface sampling techniques, just to make sure in case one does not work, we have another one. This will go from just scooping, which then has the problem. If it's soft material, fantastic. If it's hard ice, how do we get the scoop in? To things like pushing tube in to get a sample, to also actually looking at just free sample collection, have a collector plate on top of the lander, and we just collect the material that's coming down and analyze that. So this is a topic of many, many long sessions here to actually just go crazy on sampling mechanisms that you could actually think of.
Amazing. Okay, there's just one more that came in right now in the Q&A. Let's just do it because we have answered all of those questions. So Eyaftada is asking, since the ocean is almost 65 kilometers away, deep, I'm imagining, if those compounds are coming from below the surface, aren't they mixed in the water? And what are we seeing on the flyby? Is simply vapor from the pressure drop in from the ocean to space? Question mark.
Yes, some of we think that they are coming from ocean, but they could also come from the icy crust, because there is a physics behind that, because certain particles, when they are forming within the icy vent, then you have certain conditions change, and a lot of gradient conditions and Cullinan effect that can also change the nature of organics. And yes, from the core, when you have a hydrothermal beyonce, and that means you can have the thrust actually, which can really lead your species that can reach to the surface. Of course, there could be a convection process happening. Ocean dynamics play a role there as well. But also there are the bubble of gases that are coming down from the bottom to the surface, and they can actually really accelerate the motion to take the species upward. But there are certain other processes. For example, salinity plays a major role, that if you have a gradient conditions in the salinity, then which kind of species could really reach and which cannot. So many questions needs to be addressed.
Okay, thank you so much, everyone, for this amazing webinar today. We had a lot of engagement, which was great. We're well over the hour, I realize, but I think it was well worth it. I hope people agree. So yeah, thank you so much. And I'm sure we will hear more about Enceladus. Maybe next year, Jörn, at this time of year, we can do another update on the topic
Absolutely.
after the December workshop. Would be great. Would be very interesting.
Absolutely.
And all right. Thank you so much, and see you next time.
Thanks, everybody.
Thank
See you
you.
soon.
Everyone, bye then.
Thank you. Bye.
Bye. Thank you so much.